And we move on to the next term, next presentation, which is given online, again by David Lucchesi. David, can you hear us?
Do you hear me?
Yes.
So, good afternoon.
Good afternoon.
So, this presentation is on the long-term behavior of
wait,
LAGEOS
David.
II Semi-Major.
No, it's perfect.
Yes.
Now it's perfect. We see everything. You can start.
Okay, so the presentation is on the long-term behavior of LAGEOS II Semi-Major axis. Let me say firstly that our activities concerning the modeling of non-gravitational and gravitational perturbations and precise orbit determinations with geodetic satellites are part of the activities of the experiment satellite test of relativistic gravity funded by the National Institute for Nuclear Physics in Italy. And this is an experiment in fundamental physics. And tomorrow, in session 5, there will be a presentation by Massimo Visco on the results we obtained with Saturn-G and the previous experiment called LARASE, Laser Ranger Satellite Experiment. Indeed, Saturn-G builds on the dynamical model that we improved with LARASE of the two LAGEOS and LARES satellites. And in this presentation, I will focus on some of the non-gravitational perturbations, and in particular on the spin evolution and the thermal thrust effects on LAGEOS II. The long-term behavior of LAGEOS II show an unexpected change that we observed years ago and that we start to study last year. And I will show this behavior now, and then I will focus on two models, the spin one and the thermal thrust, in order to try to explain this behavior. And this is done in the last part of the presentation in order to explain the decay and rise of the semi-major axis. We performed a precise orbit determination of LAGEOS II and LAGEOS here of about 28 years using Geodyne, which is our main program for POD. The upland is 7 days. General relativity and thermal thrust effects were not modeled. Empirical acceleration as well as other parameters like the radiation coefficient were not estimated. The quadrupole was optimized with two linear trends, and of course we adjusted the state vector in order to fit the data. Here are the results of the POD for the two LAGEOS in a synoptic view. In red we have LAGEOS results, and in blue LAGEOS II. And here we can observe some spikes. They are more evident in LAGEOS I, but they are also there for LAGEOS II. And these larger amplitudes in the elements are due to thermal thrust effects. In particular, if we look to the semi-major axis on the left top, we see this strange behavior in the case of LAGEOS II that we show here better on the left. Let me say that these residuals are in the rates of the elements. And so we see that the rate in the semi-major axis over 7 days shifts from negative to positive values after about 7,000 days after the launch of the satellites, around March 2012. And here on the right, we see the integrated semi-major axis, and we see that the decay stops and starts an increase in the semi-major axis. And this is not expected, of course. And it is as if a certain mechanism is pumping energy into the system, to the satellite. So this is very interesting. The old explanation for the decay of the semi-major axis of LAGEOS I and II was practically given by Rubingham about 40 years ago, and it was explained in terms of the thermal drag produced by the Hertz-Yarkovsky effect, so by the infrared radiation, and of about 70% of the effect was able to explain, and the other part was explained in terms of the drag decay produced by charged and neutral particles. Now, based on the results of our analysis and on the models we have developed for the known gravitational perturbations, we believe that the possible explanation for this phenomenon lies in the evolution of the spin of LAGEOS II and its consequent impact in the solar Yarkovsky effect, that is, in the Yarkovsky shock effect. The rotational dynamics of a satellite is quite important because it impacts the goodness of the POD. Yarkovsky shock effect, Hertz-Yarkovsky effect, and asymmetric reflectivity, in the case of the two LAGEOS, depend from the attitude of the spacecraft, so from the spin. And their modeling will improve the POD, avoiding the current, let's say, huge use of empirical acceleration in the data reductions. The theory is not easy to be developed. We need information on the spacecraft materials, shapes, details of the structures, on the space environment, and also in the spin rate, because the equations to be solved are different in different cases. In the case of the spin of LAGEOS satellites, we build first a model in the rapid spin approximation like previous models in the literature. Then, firstly, we solved for the full Euler set of equations for the torques in the general case. And in particular, we solved the problem of a metallic conductive sphere rotating in an alternate magnetic field. And we also solved the equation in the body fixed frame in order to better describe the possible misalignment between the symmetry axis and the spin of the satellites. And we computed from the technical documentation also the satellites' moments of inertia, which were not measured before the launch of the satellites. And all these aspects are discussed and described in these two papers by Massimo Visco and myself. We have to consider four main torques: the magnetic one due to eddy currents, the gravitational torque because of the flatness of the satellites, the asymmetric reflectivity torque because of the different reflectivity of the two hemispheres, and the torque due to the possible offset between the center of mass and the geometric center. These torques provide the time evolution of the angular momentum. And here we see the results for LAGEOS II for the orientation, right ascension and declination on the top and on the bottom. In red, we have our general model. In blue, our model once averaged, so valid in the rapid spin case. And the black and green dots provides the available observations. So the predictions of the model are in agreement with the observations. And this is true also in the case of the rotational period, which is shown here in a semi-logarithmic scale. Now, thermal thrust effects are quite complex to model because they are subtle in their effects, and they arise from a non-uniform distribution of temperature across the satellite surface, and they have been attacked since the early 80s, not only in order to explain the decay of LAGEOS I Semi-Major axis, as said before, but also to explain, and we see here on the top right, the spikes in the along track accelerations observed for LAGEOS I. These are data points from the Center of Space Research, University of Texas. The problem to solve is not simple. We need a deep physical characterization of the satellites. We need to know the rotational dynamics and to account for the radiation sources. We have developed two models here, a mediated one that I will describe briefly now, and a general one. And these are the main equations of the mediated model in the eclipses and non-eclipses case. The model is similar, but not exactly like the one developed in the past by Farinella and Drogovichki. And now we can use this information in order to try to explain this, this behavior. And here we superimpose to the residuals in black of the semi-major axis the predictions of our mediated model for the solar Yarkovsky effect in red and for the Hertz-Yarkovsky effect. As you can see, there is a correlation, a one-to-one correlation, let's say, between the amplitudes, the positive amplitudes of the Yarkovsky shock effect and the residuals. So it seems evident that the change is due to the greater and positive amplitude assumed by this effect. But why this happens? An important aspect to consider in this direction is the thermal inertia of the cube corners. Here are shown three plots for the solar Yarkovsky effect for three different values of the thermal inertia: 2,100 seconds, 3,000 seconds, and 300 seconds. This last one is just to see the sensitivity of the model to this parameter. 300 seconds is more or less the thermal inertia of the aluminium, not of the silica. And in the first two cases, we see that there is a good agreement with the residuals indeed. And here we added together the solar Yarkovsky effect and the Earth Yarkovsky effect and compare the predictions with the residuals. I remember you that the Earth Yarkovsky is responsible for the decay part of this effect because it has a negative impact in the semi-major axis rate. It is also interesting to look to the geometry of this problem. Here we assume the spin of LAGEOS II in the orbital plane. On the left, there is the incoming solar radiation, and the green arrow represents the recoil force due to the re-emission of the absorbed radiation, which is re-emitted with some delay. So in the absence of eclipses, the long track component average to zero, and there are no long-term or secular effects. Conversely, in the case of eclipses, the force no more averages to zero, and we have long-term effects. And this may produce both positive and negative acceleration, as we have shown in the previous plots. And the sign depends on the geometry between the spin, the orbit, and the sun position. In general, if the delay in the re-emission is comparable with the thermal inertia, the positive acceleration are larger than the negative ones. And this is also related with the rotational period that from our predictions, from our model, LASSOS, we can see just before this transition was in the range between 1,000 and 3,000 seconds. So comparable with the thermal inertia and also with the duration of the eclipses. Moreover, if we look to the predictions of our model regarding the projection of the spin along the orbit normal on the left and the projection on the orbital plane, we see that the projections on the orbit normal goes to zero, is decreasing, while the projection in the orbital plane is increasing asymptotically to 1. There are, of course, some open aspects to be further explored. For instance, in the case of the Hertz-Yarkovsky effect, we consider only the bulk of the effect, which is produced by the perturbative acceleration along the rotation axis. So we need to introduce the other two equatorial components. And other model and non-gravitational perturbation must be considered. Firstly, the asymmetric reflectivity, which is a function of the spin, and then compare again with the orbital residuals, the predictions. And now we also started to test the goodness of the prediction of our general spin model in the current slow spin regime of LAGEOS II. So my conclusions, these non-gravitational perturbations are complex, and modeling them requires the knowledge of the attitude of the satellite, the spin evolution. We have shown that the decay and rise of the semi-major axis LAGEOS II can be explained by this combined action of thermal thrust, the solar Yarkovsky and the Earth Yarkovsky. The solar Yarkovsky effect seems to be responsible for the increase in the semi-major axis of the satellite as a direct consequence of the positioning of the spin of the satellite in the orbital plane in such a way to maximize the positive peaks produced by this perturbation. And the role of drag produced by charged and neutral particles in causing the decay would seem considerably reduced compared to what was previously thought. The thermal inertia seems to be in this interval between 2000 and 3000 seconds, probably more close to 3000 seconds. And this analysis is based on the application of the mediated thermal model, and we are interested to apply our full general model once completed. So that's all, and many thanks for your attention.
So we have an online question by Frank, so I have to read it. Astronomers monitor the thermal emission of a body, for example a planetary satellite, through an eclipse to determine the thermal inertia of the planetary surface. If the thermal emission of the LAGEOS satellites were monitored for eclipse ingress and egress, would it be possible to measure the thermal inertia to compare with the values you have estimated from CCR material properties?
Yes, thank you for the question, Frank. Yes, in principle, it is possible. I've not explained this, but there is a shadow function which models the exponential growth or decrease of radiation during the transition, entry and exit from the eclipses, which depends on the thermal inertia. So in principle, we can fit these values from the parameters. Anyway, we know that there are measurements of the characteristics of these cube corners, and probably the correct number have been measured, but we have not this information, unfortunately.